Hey, welcome back. So we covered the Cauchy-Kovalov-Skaia theorem in the last video. We're really going to get into some examples of this in action, and I don't know if I should really call it the Cauchy-Kovalov-Skaia theorem in action. Really, we're just using the power series method, which we know is valid because of the Cauchy-Kovalov-Skaia theorem. We're going to use the power series method to approximate solutions to a few PDEs. And in fact, the way that we're going to do it, we're only going to be working with flat boundaries. And even better than that, flat boundaries where the outward unit normal aligns with our natural basis. This is often the case for Cauchy problems. I mean, as always, it's named after Cauchy. Cauchy problems are basically initial value problems. That's what you want to think. So any initial value problem, you're sitting at the present, you know your position, you know your velocity, maybe know your acceleration, etc. So you know things about the present, you try to push into the future. So the outward unit normal of the present is the future is the way you can think about it. So that's really what's going to happen in a lot of these problems. If we didn't set it up so that the boundaries were not flat and the outward unit normal were not aligning with the natural basis, our life would get pretty tricky pretty fast. So if we look back at this satisfaction of the non-characteristic condition, this is an example where the outward normal doesn't agree with the natural basis, at least in a lot of cases. And if you recall, what we had to do was translate the PDE into the normal derivative direction and the tangential derivative direction. And this would change because the boundary is not flat. It would change depending on where you sat on the boundary. So you would be recalculating the PDE no matter where you were on the boundary. And it would just make your life hard. And if you wanted to represent your Taylor series, maybe in the natural basis instead of the modified basis, your life would get harder again. And so this is why we in general, we like to think about Cauchy-Kovalov-Skaia as applying to initial value PDEs. So some sort of time varying process, or they call them evolution equations sometimes. So in this case, what do we have? This is the PDE, partial t squared plus a quarter partial t plus, what is this term doing here? That's really your surface tension term. You probably don't quite remember this, but all the way back in actually the very first section we covered, section 1.1, this describes the motion of a rope dropped with fixed endpoints, right? So you've got some rope, it's got its endpoints fixed, and you drop it, and what happens is parts of the rope fall, right? But other parts of the rope are held up by tension, and so they fall less and less, and then it reaches some sort of equilibrium, which follows the catenary curve. So this is a nice dynamical PDE that describes that motion for us. And because it's nice and dynamical in that sense, we have flat boundaries, and here's our Cauchy data. That's the initial position and then the initial velocity. And then we also do have these other fixed boundary terms. These are kind of the fixed endpoints. But if I scroll down a little bit, you can see that's really our boundary here. And I'm following the steps, right? If you've forgotten what those steps look like, go ahead and look in the last video on the steps that you would use to solve a PDE with the power series method. In step one, you just kind of establish your domain and its boundary, and you kind of verify where it's analytic. Let's comment here that this probably won't be analytic there and there. There's definitely a cusp on the boundary, so it's non-analytic at the 2 points on the cusp, but you can think basically everywhere else it's analytic. And more or less, because this is a time-evolving problem, we really want to think about the present, which is this line here, as our boundary. We're not kind of thinking about the fixed endpoints as too important of boundaries for us to solve our PDE at. What we're actually going to think about is, hey, can I establish a point right here, call that T naught, X naught, well, we know what T naught is, T naught 0, call that point, can I establish some sort of local, maybe power series solution within that range? And so because this is flat boundaries, if we took that point right there and we pointed outwards, that's a very natural outward unit normal vector. It's the vector -1, 0. This is the time direction, by the way. So the negative time directions are outward unit normal. And we're going to choose that point right in the middle, which was 0 pi, so pi for x naught. And we're going to choose that point because it's safely in the center of an analytic place. Like, we want to avoid the two corners here, so might as well grab the point right in the middle of them. That's happening at time 0. We're going to, like I said, we're really approximating the solution in that sort of region, tiny region of that point. So moving to step 3, we want to decide the order to which we're going to approximate. Let's just decide on quadratic for now. So we'll fix our high Taylor series terms at n equals 2. And then in step 4, it just says, hey, if we decide on n equals 2, let's make sure we know what that looks like. So I go ahead and write out the full Taylor series in my x and t dimensions all the way out to quadratic terms. This is what they all look like. In the last video, I kind of went through this modified definition where we just are paying attention to those two powers as well as its factorial. There's two powers here, but because each one individually has a power of 1, this is really divided by 1 factorial. 1 factorial, so it's divided by 1. There's a 2 factorial, and a 2. There's a 1 and a 1, a 1 and a 1, and then zeros, right? So it's really powers of zeros on that first term. So that's what it will take to write out the full Taylor series up through quadratic terms. So the question becomes, okay, can I, right, so the real power series method consists of finding coefficients. So I've got that one, that one, that one, that one, that one, and this one, basically by any means necessary. Okay, so can I find those 6 coefficients by any means necessary? The whole idea is that the Cauchy data will give me this and this. Maybe I'll write that down. By definition, that has to be given to me. That's the Cauchy data. And then let's note that my tangential direction, right, if my boundary was this kind of sort of square looking thing, the normal direction pointed downwards, the tangential direction points to the right. So that's really partial x. So tangential derivatives can act on the Cauchy data for free, which means I can perform partial x on the Cauchy data for free. So I can perform partial x on phi for free. That's going to give me partial x of phi. I can perform partial x on partial t for free. That's going to give me partial t partial x. And in fact, I can perform partial x twice on phi for free, and that's going to give me partial x squared. So all of the terms in yellow, geez, this is inverted, so maybe that's purple for all of you. All of those terms in purple come from tangential derivatives of Cauchy data. Okay, so the Cauchy data was the initial collection of data that I was given. I'm able to produce tangential derivatives on that, and that's going to fill out 3 more terms for me. So really, all that I'm going to be missing is this very final term, partial t squared, the acceleration term. And I'm going to have to look at the PDE for that term. So the PDE gives final term. So that's really what I'm going to be thinking about. That's really kind of how my steps describe it as well, but I wanted to describe this all in words for all of you before we got into it. So we're going to find all 6 of those coefficients doing everything that I just kind of described to you. So in step 5, we make clear what is our normal and tangential derivatives, which I kind of already talked about. So the normal direction is -1, 0. Tangential direction is 0, 1. This is in the variables x and t, right? So this is actually t there and x there, t there and x there. So I have negative time direction for the normal derivative, positive x direction for the tangential derivative. And if I want, I can omit the minus sign on the whole negative time term here. So that's totally okay. But what I get then is I can calculate, as I said before, from the Cauchy data, this term and that term. That comes straight out of the Cauchy data. So there it is. There's the first one. There's the second one. Where am I taking those numbers from? Let's go back. They're coming right from the Cauchy data. So because my boundary is the part where t equals 0, I'm going to look at those 2 expressions that was given to me, and I'm just going to evaluate at the point that I've decided for x. So I'm just plugging in pi for x here and pi there. So I'm getting values there and there for the 2 Cauchy data terms, which I guess gives me 6 and 0. And then in step 7, this is where I'm going to construct the terms here, where I can take tangential derivatives of the Cauchy data for free. So these 3 terms I can extract for free from the tangential derivatives on the Cauchy data. So that's going to happen in step 7. If I go to step 7 here, see I can act as many powers of the tangential direction as I want, and I do that on the Cauchy data. Let's recall the Cauchy data. So I'm taking as many powers of derivatives in the x direction of those 2 terms as I want to find as many derivatives as I need. So like the first one will be 5 plus, or sorry, the 5 will disappear, I'll have 1 plus pi, and I'll have a cosine. And in the second case, I'll just have a 0. So if I go all the way back down here, there's my 1 over pi and cosine. And then 0 in the second case. And in fact, I can take a second derivative of the initial boundary term, which was this one. So I can take one more derivative of that, and I get negative sine x. So that's me extracting as much information I can from the boundary. And then if I evaluate those at my initial conditions, 0 and pi, we're getting 1 over pi plus 1, 0 for the xt term, and then 0 for the x squared term. So that's given me, so far, it's given me 1, 2 coefficients, 3, 4, 5 coefficients. I'm only missing one more coefficient from my power series The last coefficient I'm missing is this one, 2 derivatives in time. And that one, the top, right, it's always the top derivative. Always top derivative, normal to boundary. As well as some others, right, if you go even higher power than 2, but it's always the top derivative normal to the boundary, and higher powers of that you're going to have to extract from the PDE. So what's really useful is if I go up to my PDE, I was looking for partial t squared, that's my top derivative normal to the boundary, and there it is. Right, so kind of the idea now is the PDE, if I rearrange, I know all the other terms. Right, I know all these other terms. I've calculated that from the Cauchy data. I've calculated these from the Cauchy data. Everything else is given to me. So because I know everything from the Cauchy data, I'm able to find the last term from the PDE by just evaluating everything, or rearranging it so that I've isolated the second derivative in time, and then evaluating everything from the Cauchy data that I've already calculated. Now I've already calculated that this is 0, and in fact, this is 0, this part's non-zero, but everything else is 0 there. So it turns out that second derivative in time is just this negative 1/2. And so you find the very last coefficient is negative 1/2. Boom, you found all coefficients you need. All you do at this point is actually evaluate all of them in. So you plug all of these into the Taylor series, and what we're left with is a nice little quadratic polynomial in time and space, right? Because it's a PDE, so it's going to depend on both time and space. So that's going to be an approximation, and I can plot the approximation against the true solution. There you can see me. That's kind of the initial height of the rope, and then as you watch it fall, the rope kind of does this. You can see it reach equilibrium. So that's the true solution, and here's my approximation. And I'm sure a lot of you are looking at me like, what the heck, Evan? That is a stupid approximation. Kind of agree with you. Stupid approximation up to this far in time. So we weren't actually looking for an approximation for the entire future. What we were looking for was an approximation locally. Now, this is a very important word that mathematicians use. This means in a very, very small region, we centered the power series at, around where we centered the power series. And when I use this word region, that's a region in time and space. So what is a small region in time? That would be something like, instead of, this is like time 0, 1, 2, 3, 4, 5 seconds, instead of that much time, we're thinking, let's make time a lot smaller. So a small region of time is 0 to 1/2. Small region of space, that's where we center the power series in space. Let's just add 1/2 to either side of our points in space. If I restrict time and space to those directions, those tiny regions, now we can see the comparison of the approximate solution with the true solution, and you can see it really does actually a very good job of approximating the solution. This is what it means to be local, and we want to be careful with power series methods. They are always a local method. They're never going to be global or even, outside of some very small range of where we center things. So that's what we get, and we just want to be clear that it's a very local approximation. You can learn a lot about a solution from a local approximation, so just make sure you realize what your approximation actually does. Now let's just move on to a second example. Make our lives a little harder and go through cubic terms. And actually, you're going to make our lives harder again because we're going to be nonlinear. I guess we were nonlinear in the last case, but the nonlinear terms didn't play a huge role. So we're nonlinear. We kind of have this like Laplacian-esque thing, but it's been modified by a nonlinear term in phi. So Laplace's equation, but now it's been modified with the nonlinear term in phi. And here's my complete Cauchy data, right? So Cauchy data, because I'm working, where's my boundary? My boundary looks like it's in the y direction when y is equal to 0. So my Cauchy data needs to include the case when y is 0, but it also needs to include a derivative in y when y is 0. That's what I need to have some sort of all lower powers of, right, because that's second order, all lower powers in the direction of y, which is my boundary. That's going to be the Cauchy data. So there's my Cauchy data. And then we are going to note that the PD is second order and the boundary is flat. I haven't actually drawn the boundary here, but there it is. It's, well, that's the domain r times r plus. The boundary is just r cross 0, which is, the real number line more or less. So that's a very flat boundary. And what is its tangential direction? That's just the x direction, also known as partial x if I'm doing a derivative. My outward unit normal, partial n, is just in the y direction. So we kind of have the same sort of thing going on at the boundary here as we did in the last problem. we're going to choose a natural boundary point, right? We need to choose some point in here that we're going to center our Taylor series at. So that's everybody's favorite point in R, 0. I hope you say that. Maybe you say 1. My favorite point in R is 0. So we're going to start at the point 0, 0. It's going to be our point that we center the Taylor series at. And as I said at the top, let's go through cubic and make our life a little hard. So power series, or the general Taylor series through cubic terms, is given here. Doesn't look great. It doesn't look terrible. But then we just want to make sure that we know what's going on here. These are the coefficients that we need to find by any means necessary. And before I get too far into it, let's recall that the normal direction is the y direction. The tangential direction is the x direction, which means our Cauchy data will be this term and this term. That's our Cauchy data. So we know it because the PDE gave it to us. So that's free. The PDE gives us that for free. Now, we will always be able to take as many of these as we need. So Cauchy data is always in the normal direction. The number that you can take as many as you need is always in the tangential direction. So Cauchy data is in the normal direction. Derivatives I'm allowed to take are in the tangential direction. So that's why I'm looking at the tangential direction there. From this, I could go tangential, gets me to partial x. A second tangential will give me to partial x squared. A third tangential will give me to partial x cubed. That's all coming from the initial phi. And then if I start with an initial partial y phi, one tangential will get me to partial x, partial y. Two tangentials will get me to partial x squared, partial y. And so all of the terms I've circled right now, I will be able to obtain from tangential derivatives of Cauchy data. The final ones that I will circle now, these last few terms, 2 derivatives in y, 1 in x and 2 in y, and 3 in y. These will all need to come from the PD itself. And you'll notice, where did that start? It started at 2 derivatives in y, because the PD itself, the boundary is when y is 0, and the PD itself has 2 derivatives in y as the top order of the PDE. So it starts with 2 derivatives in y. You can calculate higher derivatives out of that case. So that's how we can kind of split up all those coefficients. Let's actually start with the Cauchy data terms. Those are pretty easy. You get them for free. It's always in step 6 technically, because I was kind of already talking about our tangential and normal directions. But in step 6, we can calculate the Cauchy data. Now recall, that's just the boundary conditions the PDE is given to us. So this term and that term, I just evaluate at the center of the Taylor series that I've chosen. So 0, 0 in this case. We can evaluate those. So that's e to the minus 0 squared over 2, which is 1, and cosine of 0, negative cosine of 0, which is negative 1. So those are going to be my Cauchy data terms that I get for free. And then let's recall, I can take as many tangential derivatives, here that's partial x, as I want of Cauchy data. So that's me coming down here and saying, let's take 1, let's take 2, let's take 3, and then let's also take 1 of the partial y term and 2 of the partial y term. So I get a total of 5 possible cases, because I can go up to 2 or 3 terms on either of those if I want to. So I can get 5 more terms of my coefficients out of just taking tangential derivatives of the Cauchy data. When I perform those derivatives on the Cauchy data, right, so it's me performing partial x's of these 2 cases, partial x's of those. What do all of the terms end up being? I get negative x e to the minus x squared, I get sine, I get x squared minus 1 e to the negative x squared over 2, I get cosine, I get x3 minus x squared e to the minus x squared over 2, whatever. You all know how to do calculus, or I should hope so by now. So you're just doing a lot of calculus here. But now you're evaluating at 0, 0. So we evaluate those at 0, 0, we get 5 more coefficients. So far we've calculated 1, 2 from the Cauchy data, plus another 5. So 7 coefficients from Cauchy data plus tangential derivatives. We're still missing 3. There's going to be 3 terms that we haven't accounted for yet. And those all have to come from the PDE itself. So if I jump back up to the PDE, here it is. It's going to be to my advantage to expand that Laplacian. That's 2 derivatives in y plus 2 derivatives in x plus phi squared is 0. And even better than that, let's go 2 derivatives in y equals negative 2 derivatives in x minus phi squared. Now this is good because I've actually been able to calculate all of these from Cauchy data and or tangential derivatives of Cauchy data. That means that all the information on the right-hand side can be used to give me the information on the left-hand side. And the information on the left-hand side is what I need right there. It's that coefficient. So let's go down, step 8. And you can see I've done exactly that. I've isolated two derivatives in y to the left-hand side. And at this stage, let's recall the third order Taylor series also needs partial x partial y squared and partial y cubed. So what I can do is I can actually take this equation and I can take a derivative in x of both sides. So I'm going to take a derivative in x of both sides, give me partial x partial y squared, and I just have to act that on those two terms. There's my little chain rule showing up. And I can also take a derivative of y in both sides. If I take a derivative in y of both sides, I get partial y cubed, and then I just go ahead and take a derivative in y of both sides on the right, negative partial x squared partial y, 2 phi partial y phi. Now what's interesting is it doesn't necessarily feel like it right away, but in fact all of these terms on the right-hand side we've already computed. So we've already computed in steps 6 and 7. So because we've already computed those, we actually know everything on the left-hand side here. All we have to do is plug the values in. That's what I do. I just plug the values in that we've already found out. So this entire section here. And you find out that two derivatives in y coming from that equation is 0. 1 in x and 2 in y coming from this equation is 0. And 3 in y coming from this equation is 1. So there's my last three coefficients. And then I jump back, I mean, arguably to step 4 if you want to, but I actually plug all of the numbers in to my Taylor series that I've just calculated for. Plug them all in, and you get an approximation. So here you plug them all in, you get the following approximation. 1 minus y minus 1/2 x squared plus 1/2 x squared y plus 1/6 y cubed. Okay, let's see how good this approximation is. So if I jump down to the true solutions in this grayish color here, and then the approximations in the cyan. So I got my approximation in the cyan there. It maybe doesn't look awesome, but what we can think about is, once again, Taylor or power series approximations are local to the center. And where's my center here? In this case, that's 0, 0. That's this point. We're in the middle. So that point, you imagine if I just zoomed in on that section, my approximation gets a lot better. So if I do zoom in on that section, now you can see the approximation and the true solution are so close to each other. And in fact, this isn't even too bad. I went up to 1.5 in the height here, x's and 0 to, or -1 to 1 and y and 0 to 1. So this is a fairly broad range, even just at cubic terms of an approximation. Okay, and then there's one final example in which I do comment that we do not follow the step-by-step procedure. So the last two cases we had that step-by-step. We can actually make our lives a little easier than that in some very nice cases. So the first order Cauchy problems, that's really this setting where, you know, the left-hand side of the PDE has already been solved for the outward unit normal derivative. So the left-hand side is first order outward unit normal derivative. Which means that the right-hand side only contains derivatives, only has tangential derivatives. So your life can get quite easy when you have a Cauchy problem of this form, in the sense that if you just wrote out phi as a power series, you know, of any order, it looks like this. This is just characteristically the power series in any order. I mean, if you were working in higher dimensional space, then it wouldn't look exactly like this, but in 2 dimensions is what it looks like. It's written out in any order. What we can see here is we have some partial derivatives on phi that show up in the time direction. And we actually know what the partial derivatives on phi in the time direction are. They're just 2 partial derivatives in the x direction. So you can replace each partial t, really to the n, phi with partial x to the 2n phi. So that makes your life really easy. That's just because the PD itself told you that you can replace it. So you look at the PD itself, it tells you can replace your normal derivatives with whatever's on the right-hand side. And that simplifies our power series to the following. Right now I'm only considering derivatives in x. And then I want to center this at the boundary. Well, the boundary here is when t is 0. Okay, so the boundary is when t is 0, but the boundary is exactly my Cauchy data. There it is when t is 0. It says, by the way, phi at that point is actually f. So you just replace phi on the boundary with f, its actual boundary value, and you take as many derivatives in the x direction of f as you need, and that's your solution. So this will always solve. Will solve, you know, the 1 by 1 dimensional heat equation over all space. Right, so there's a nice formula for you that the power series method can give for solving the heat equation over all space. And if you want a really nice approximation, if you're going to truncate this somewhere, if you want an approximation near some point, use that point for x0. So we can do that here. Give an example where f is x e to the negative x squared over 4. Let's choose 0 as our initial point. And then let's truncate at 25 terms. So what I'm saying is, like, let's construct this power series and plot it. We can just do that on a computer. It's not too bad. You obtain the following plots. So what's in cyan is the approximation. What's in gray is the non-approximation. And it's almost so hard to know where the non-approximation is. I'll highlight it here. So these terms I'm highlighting are the true solutions, and everything else is the approximation, which means that for a long time, the approximation and the true solution agree. Right? So like all of these, the two plots are covering each other up. So they only start to diverge a little bit later. So you actually get really nice approximations when you have these nicely behaved problems. Anyway, I'm going to stop there. Next section will be finite difference methods. I hope that sounds interesting, and I'll see you then. Bye.